Today we will be looking at the problem of search. Now this is a very important subroutine that is used in many algorithms that we will encounter in the course of this whole uh, algorithms course. So what is the problem? So the problem basically says that you have been given a set of numbers, say a1 to an, the set is S, and some other number b, and the question is S, sorry, is b in S. In other words, we want to design a efficient algorithm to check if b is in S. Now, as you can see that to ask this question whether an element is present in this set or not, this set doesn't have to be a set of numbers. It can be a set of anything. But a crucial uh, property that a number has is that we can use two numbers to check which one is bigger and which one is smaller and so on. And that's why this numbers takes an additional value. So you will soon see in the rest of this lecture that how this fact that this b is a numbers, real numbers, that is used. Okay, so but before I move on any further, one thing that you should always ask whenever you have to do an algorithm is how is the input given to you. In this case, the question is how is the set B given to you, right? So, how is the set S, sorry, not set B I told, it is set S, how is the set S presented? Now, there are multiple ways in which the set S can be presented. Basically, they can be stored in particularly certain way, the set, or in general any data can be stored in some particular structure which we call data structure. Now these data structures tends to support some operations, some kind of operations. Some operations might be cheaper than the others, whereas some operations might be costlier. So we will be seeing a number of such operations, such data structures throughout the course. But two of the most important data structures are the linked list and arrays. If you have done some course in programming beforehand, you possibly have seen both of them. But just to recap, let me just go over what a linked list and what an array does and some properties of them. So particularly, so what is a linked list? So if I have to store say the number 1, 4, 2, 6, 8 and 9 and 7, how can I store it? So one option is that I store this number 1 in a particular place and I put along with that 1 another holder that just contains an array, an address to the next slot 4. So this is an address to the next where the next number is present. Similarly, at 4 there is a right along with 4 there is a register that contains a another address that points to the next number, say 2, and likewise I can define 6, 8, 9 and so on. Now note that although I have written it in this nice linear form, it doesn't have to be. So maybe you can say what happens in the last thing. The last thing might goes off to here in the grounded in the. Oh, sorry, I made a mistake. I had to put in 7 somewhere. Now, how do I put in the 7? So, one option is to of course put it at the back, but I can put it anywhere I want. For example, if you say that you want to put this number 7 somewhere between 4 and 2. How do you do it? All I need to do is that I put the number 7 and I make some small changes. I will remove the array address from 4. I will just add this 4, redirect this 4's address to 7 and redirect the 7's address to 2. And note that I have now been able to insert this number in this array. In this linked list. So this is called a linked list, right? And the useful thing is that you can add or delete numbers or elements rather in order one step. As you saw just now, all I need to do is that just read out the addresses and you can edit. For example, if I want to remove this number 6, I want to remove this number 6 from this set, then what can I do? All I need to do is that I just remove this number 6 and all I do is that I redirect this address of 4 of 2 to 4 to 8 and I am done. But this also has one problem. What is the problem? Problem is that now if I want to go and tell you that what is the 4th number in this linked list. Now you don't have any idea of the 4th number. The only way you can go is that you can go to the first number, then you count, oh, okay, this points to 4, the 4 is the second number, then go to here which is 7 which is third number, and now here you go and to 2 which is the 4th number. So to reach the 4th number you have to traverse the linked list from the starting to 4 different places, along 4 different places, right? So in other words, we can say that if you have to access the ith number, you have to go for the, in the worst case, you will require I steps. Not worst case, actually you will require always I steps. And if you want to look at the ith number from the end, okay, again there is no way of doing it. There is a way of converting this linked list into what is called a doubly linked list, where you can have addresses going both directions. This 4 has an address, say, which can get connected to the previous one also. So this is kind of called the doubly linked list, where every element has a pointer or address to the next number as well as to the previous number. So every number has a register, it has two things. One that is talks about where the previous where the next number is, and the one that says what the previous number is, and so on. So you can do it using the doubly linked list, but again, so using the doubly linked list, you can go to the 5th number from the back or from the last, but that also requires 5 steps. So in other words, traversing is hard. So going and finding out the ith number is hard, right? So this is a problem with the linked list. Now we have another one which is called the arrays. What is an array? Array is a very simple one. You have a big consecutive set of cells, and in each cell you are writing 1, 4, 2, 6, 8, 9, 7, right? And you have a start point, and you usually don't have an end point, but that's fine. And so we call this one and say array A, and the array I points to the ith element. It doesn't point to, I refer to it. Array I is the ith element. So this one is the, so 1 is stored in the first position of the array, 4 is located in the second position of the array, and so on and so forth. So in this case I can say that A 4 is 6. Now some people might start from this talk about the first index not as 1 but as 0. In certain programming world, this first position is referred to as the 0. So it starts from A0, A1, A2, A3. In some places it is referred to as 1. So A1, so it starts from A1, A2, A3, A4, and so on. But anyways, for our purpose, both of them are kind of similar, and we will mostly be talking about starting from 1. So 1, 2, 3, 4. But what are the nice properties that it has is that it has a what is called a RAM, or a random access memory. Why? That means that if I tell you that give me the fifth number, you don't have to traverse the array from the left to right. You can just quickly jump to the fifth position in one step and produce me the fifth number. So the fifth number is 8. So in order one time or step, you can find out what is the ith position, what the element stored in the ith position is. But the downside of this array is that adding and deleting is very hard. For example, say if you say that, oh, I don't like this number 6, I have to get rid of the number 6 from here. What do I do? Okay, you can say that, oh, why don't we just erase that? But erasing is problem. Arrays doesn't allow erasing from the middle. The only option that is there is that after you erase, you copy the one which is next to it, which is 8 here, and then you again erase the 8, then you write the one that is next to this empty cell, which is 9, and then you again erase this 9, and then you copy this number rest to this thing which is 7, and then erase 7, and then there is nothing beside it, and so we stop here. So similarly, if I have to add something, say if I have to put back the 8 between put back this 6 between 4 and 2, then I have to kind of create a gap here, and the only way I can do it is that again do the whole process by first shifting this stuff by some quantity and one by one copying this whole thing until I can create a position or empty cell here, and then I can add the number 6 over here. So you can see it takes a lot of time. So addition and deletion is costly. Now these are the two very important things. The addition and deletion are costly. Okay. So in one spectrum or one place we have this linked list or the doubly linked list where addition and deletion is very easy, order one number of steps, but going to the ith place is very hard. And the array, going to the ith place is very easy, but addition and deletion is hard. So here is a kind of a wrap up, that for linked list using order n steps in the worst case to find what the ith element is. In other words, if I is n, then you will take the order n steps. But this can be done in order 1 in the case of arrays. And on the other hand, to add or delete in a linked list, it is just order 1 step. But in an array, it might take order n steps. So this is what, these are the two kind of data structures. There are a lot more other data structures that we can think of, or we will be studying in the next few lectures. So here I have left the question. If you remember the question that was there, that if you have been given a set S and a number B, can you come up with a efficient algorithm for checking is B in S? Now I have not answered this question, but I leave it to you guys to prove that if S is given as an array or as a linked list, sorry, there is a mistake here, it should be linked list, then the time to find whether B is in S can take order n in the worst time. Note that I am talking about the worst time and not the best time. The best time in either of the cases might be just order 1, but the worst time can be order n. But one can ask, what happens if the array or the linked list has some other property, if the data is stored in some nice way. For example, if say the data structure that is storing, so data structures, as I told you, are these arrays, linked lists, they are examples of data structures, but you can have other data structures. For example, an array that only allows the data to be stored in a particular way is a special kind of data structure. So here we are talking about what happens if the data structure only allows the elements of S to be stored in a certain way. For example, what happens if the S elements are stored according to the increasing order? So here say note that I have actually used the fact that the set S is a set of numbers. So there is an ordering and so on, right? So what happens if the S's are stored in a increasing order? I mean, again, increasing is not something special. You can have increasing or decreasing. But the fact is that it is stored in some nice order. Then how can you do it? So I will be going to tell you how you can then quickly search whether a number B is in S or not by when the set S is given in an array. If the set S is given in a linked list, this particular extra information that the S's are stored in an increasing fashion does not help. Try to convince yourself why it does not help in the case of linked list. But in the case of arrays, so in the case when the set S is given in array form, this can be very useful. And the way to find it is what we call as the binary search. Okay. So basically what do we have? Say I have these numbers in an array. So let me just draw the array first. and they are stored in some number 1, 3, 9, 10. Note that they are all stored in a increasing or decreasing fashion, right? 15, 20, 23. Now I want to check if this number is 13 in this set. Okay, the set S is of course this set of, this is, you can think of this set or the array, right? I will use S to denote both the set and the array assignment. So the idea is that you start with two different pointers. The first pointer, start with one pointer, and then the pointer is say here. Start with the pointer which is at the last. Again, you can start with the pointer which is in the beginning. Now, okay, I have not written this numbers 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is nothing but A9, right? You are now pointing out, sorry, not A9, S9. You are looking at the ninth thing. But what you do is that, okay, you check, is S is 13 bigger than or equal to S9? In this case, it is not, right? You get the answer no. What does it mean? It means that this number 13, if at all it present in this set, must be in the left hand side of this pointer. So what you do is that you jump straight from S9 to S9 by 2. What is 9 by 2? Say is 4. So go to, you remove it from here and you jump straight into and look at S4. Okay. Now question is 13 bigger than or equal to S4? And here the answer is yes. What does it mean? It means that this number 13, if at all, must be between this between S4 and S9, right? Between the 4th index and the 9th index. See, here I am assuming the fact that this set is in an ascending format, the increasing format. So what do you do? So you had already seen that this is in S9. You have already seen that this is in S4. So this was S4 if you remember. So what you do is that you go to the middle of it. What is the middle of it? 9 plus 4 by 2. And what is this? This is the number 6. Now the question is that is 13 bigger than S6? And basically you mean that you have shifted from here and you asked here. Now here, if the answer would have been no, it would mean that 13 must be on the left hand side of S6, and in that case I would have known that it is between S4 and S6. But in this particular example, I know that the answer is yes, which means that S6, 13 if at all must be on the right hand side of the 6th thing, and we go to S6. And you go for one more step, right? And basically you go to next step is 6 plus 9 by 2. So if I partition over here, the next thing you do is that what is 6 plus 9 by 2? and this is 7, right? I hope I am doing the calculations right. Yeah. So, you go to the next step, which is S6. Is 13 bigger than S7? And here you would get the answer no, which means that this 13, if at all present, must be between S6 and S9, S7, right? And which we understand cannot be possible because S6 and S7 are next to each other, right? So, we know that 13 is not present here. Wonderful. So, I have produced an algorithm that would somehow manage to find, I have not given you a proof of it, that this algorithm will work. Now, you should think about why will this algorithm work all the time, first of all. Secondly, what is the number of steps that we have made to use? Again, I am not going to give you a formal proof of this thing right now. I leave it to you guys to go and fill in the gaps. But the basic idea is that initially, look at these pointers, right? In some sense, I had kind of a 2-pointer situation. I first had a pointer here I can think of and a pointer here. Then I shifted this pointer to from here to here. Then I again shifted this pointer from here to here. So there was an 2 pointers, one ensuring the lower side and the one ensuring the higher side. And I had kept on dividing the distance between high and low by a factor of 2 every time. High minus low in this case is n. If I keep on dividing the distance between high minus low by factor of 2 every time, it goes down to constant or 1 in log n steps, log n base 2 steps. So, this binary search algorithm, so this is called a binary search because you are doing it with the two kind of thing questions, like is it less than this or more than this kind of stuff. So, you will be getting it in this in log n steps. So, here is the pseudocode of the binary search algorithm. I am putting it out for you guys to go and verify that this binary search algorithm pseudocode indeed does what we wanted to do. Okay. So, here note that there is this two algorithms, L and U. So, these are the 2 pointers. So, L is basically the one that points to the lower end of the indices and U is the point to the upper end of the indices and kind of says that is it there in between these two. Okay. You always ensure that the set B, element B is between these two, U and L. I would like you guys to think and try to give a formal proof of the correctness of the algorithm and the proof of the running time of the algorithm. How to get a formal proof of it, we might see it in a later video or in our online classes. But for now, I would like you guys to go and think about formalizing the whatever I just now told. So, basically what I told is that the binary search algorithm on an array of length n takes order log n steps. And this cannot be done in the case of the linked list. It all, first of all, I have not told it, it always finds the right answer in within log n steps. It always finds out. But I want to focus on one more problem. So we started with the case when the set was not sorted, and then we saw that we take at least n number of steps, and then we told that okay, what happens if the set is sorted, or its set is present in a sorted way. Then I convinced you guys, or tried to convince you guys, that binary search algorithm can find or answer is B is in the set or not in order log n steps. Now question is that, can you do it better? Is there a more efficient algorithm of doing it? So in other words, if it is been present in a sorted array, I mean, who told you that you cannot have an algorithm better than log n? So this brings us to another important concept in algorithms, to proving log n, lower bounds, okay, or called the hardness of algorithms. Okay, so here we are going to prove that you cannot find an algorithm which is significantly lower than log n number of steps. So there are various tricks. So finding lower bounds of algorithms is actually the hardest problem in algorithms. Okay, it is the hardest problem in the subject of algorithms, complexity, and so on. We will see more of it later on. So people have come up with very creative and beautiful ideas. So let me present you two kind of ideas. So first of all, the idea is called this using decision tree. What is a decision tree? So the decision tree is, so whatever we are doing now is that I have been given the set S and I have given the set B. And what is the first thing you will do? You possibly would like to, I mean, there can be any algorithm, note that. I am not saying that this binary search algorithm, somebody can come up with some crazy algorithm, okay, and I have to prove that however crazy that algorithm may be, if that algorithm finally outputs the right answer, namely can output is B in S, then it must have made log n number of comparisons. Okay. So what is the, so somebody has given me an algorithm. Let's call this algorithm ALG. Now in that ALG algorithm, what this algorithm does, it must have asked or compared B with some particular element, right? So maybe the B has been compared with or less than or equal to, maybe I will just add this question mark, with say S I. I don't know what that I is, some I. And here you could have got two answers. Either you could have got yes or could have got no. Right? And if the algorithm got yes, it should have asked some other question. Maybe is B less than or greater than with S I plus 1. Or maybe if it had got no, it should have asked some other question. Is B less than or equal to S1? See, I don't know what this algorithm is going to do. But what I know is that depending on the answer of the first query, it must have decided previously already that it is going to make what queries next. Similarly, depending on what answers it gets when it asks this question in this node, it will get two answers, again yes or no. And depending on what answers that he gets, he will make another two queries. And similarly here, if the answer was no, he would have got again, he would have made this question and he would have got two answers, yes and no, right? And basically by doing so, we will be basically creating, if you can also recollect from your discrete math course, this looks like a binary tree, right? I mean, binary or not is not the important part, but it is a tree. This tree is what is called a decision tree, because it's like depending on what value you are getting from your query, you are going to make two decisions. Either you have to make a decision of what questions that you will be asking, and so on. Good. So I can view any algorithm in this way. Any algorithm will have a corresponding decision tree. That decision tree may be as crazy as it can get, but still it will have a decision tree. Now, when does an algorithm stop? An algorithm stops if it comes to the bottom of the leaves, right? At that point, this algorithm must have, so it has come here with a lot of yes, no answer that it has got, and this one, by then, the algorithm must have understood the solution. Note that the algorithm is always correct. What does it mean? That at this point, the algorithm, whatever it goes to output, must be the correct answer, right? So at this point, maybe he outputs the fact that, oh yeah, actually B is in the set S and it is in the ith location, it is in the 100th location. This can be a statement that it can output, or it can also output in some another leaf that no, B is not in the set S. So every leaf therefore ends up with an answer. The answer can be that B is not in the set S, or B is in the set S and in this position. Fine. By the way, although I have drawn this tree in a very complete tree, it doesn't have to be complete tree. It can be a arbitrary tree. Maybe this particular uh, uh, maybe this particular part of the tree just stops right over here, and here only it can output, oh, B is in is uh, so B is equal to S5. Maybe it can say, or maybe it can, for some other tree, it might go for some other length, and finally it will output that no, B is not in this set S. Irrespective of that, at any leaf, the output will be either B is not in the set S or B is in the set S in this particular location. Fine. Now, the next question is, how many such answers are there? Okay, let me see. So, I will ask how many possible answers. Note that this B can be there in any of the n locations, or it might not have been there. So the total number of locations is, total number of possible answers is at least n plus 1. So in each leaf, exactly one answer could have come out. It means that the number of leaves must be more than n plus 1. Now coming back to this old tree, whether this tree is a complete tree or not proves that if number of leaves is n plus 1, then the depth of the tree this implies must be more than log n. Okay, the depth is the maximum length of this path in this tree. So this is the depth, right? Maybe one particular edge is the one particular say maybe one particular path is small, but if as long as one path exists which is very long, that is the depth. Note that this length of this longest path in this tree from the root to the leaf is actually the worst case running time of the algorithm, right? The shortest path from the root to the leaf is the best case running time, but the worst case running time is the longest path. So if you once you prove that the depth of the tree is log n, it means that the worst case runtime of the algorithm alg must be more than log n, right? So this is basically the main argument of binary, the lower bound of binary tree using decision tree. Fine. Any algorithm can be looked as a decision tree, and the depth of the decision tree is the worst case running time. And by looking at the number of leaves, you can decide on the depth of the binary decision tree, or which is in other words, you can get a lower bound on the worst case runtime. Now, okay, one thing that I have kind of not talked about, or I kind of lied to you, is that I started with the question that I was just interested in is B in S. But somewhere in the middle, I kind of told that in the H leaf, you basically will have to output which location is B stored. So that was not the deal with the algorithm. So is it possible that there is an algorithm that does not output which location is a particular element stored, just outputs is B in S or not? So in that case, of course, the number of possible solutions is no longer n plus 1, it goes down to just 2. So this whole argument doesn't go through. Okay, I am not going to say much. Think about it. Such kind of algorithms will also take log n steps at least. Think it in this direction of the decision tree. Okay, note that every node here is comparing B with something. Use that fact to prove that irrespective of whether the algorithm is outputting the index where B is located or not, still it will require log n steps. Okay. So this is a very important algorithm or both binary search is a very important algorithm, as well as the decision tree lower bound is a very important concept to grasp. So there are quite a number of related questions. I have kind of written them down. They will be presented to you as a so you could take them as a exercise and try to solve it. So basically, given a set of set S not sorted, can you produce the algorithm that finds the maximum now of the set, okay, and proves that this n plus 1 comparisons are necessary. So, here n plus 1 is important. I am not talking about in the asymptotic notations. I am really talking about n plus n minus 1. I am really talking about n minus 1. Similarly, uh, if I ask you to find out the maximum and minimum of the set, then how many steps do you need? What happens if I ask you to find the maximum and the second maximum? Then what? Give me the algorithm for finding it. And on the other hand, you should try to prove lower bounds for all these questions. So these questions may be discussed in the online uh, classes. Yeah. Now, there is some more. So we talked about arrays, we talked about linked list, and we talked about sorted arrays. But then there are other data structures in which the data could also have been stored, and where you might be able to use some nice properties of the data structure. So one such is called the binary search tree. There are zillions of data structures in the world, some of them very specifically designed for a particular problem, particular algorithm, and so on. So binary search tree is a pretty powerful data structure that has a lot of applications. I don't want to say too much about it. I can just say that binary search tree is a mixture of the array and the sorted array and the linked list. You are I mean, advised to look up the definition of binary search tree from the internet or the Wikipedia and study the worst case, average case, best case runtime for finding whether a particular element is in the set or not. This is how we will be doing many of our videos, where I will be asking you guys to go and check out some particular notions, definitions from the internet, and I would expect that you guys will be sincere enough and do it accordingly. Okay, thank you.